Record. Okay, so as you can see, top score last year, 696. The average was 77%. Yeah. And this is kind of what it looked like this year. 3 A's, 21 below C's. Yeah, I mean, it's a tough test. It's, you know, as I was going through it this morning, again, some of the questions I did write, and I like it when I write a question, I go, that's a good question. It made me think, you know, and we'll go through it and we'll explain. This is really good learning tool, so ask questions, please, so that we can, I want you to get your heads wrapped around this. Okay, so number one here, all of the following affect the exposure rate or intensity of the primary beam, except if I increase or decrease kVp, does it change any of the intensity? Yes. If I change mass? Yes. If I change the size of my exposure field? Mm-hmm. So the answer here, and the key words, primary beam, if we have the primary beam here and here, we would have 1,000 photons, arbitrary number again, in both places. So SID does not have an effect on that. Now, if it said intensity of the IR exposure, then it would have an effect on it, right? Yeah, I did it on time. What effect would increasing SID from 40 inches to 50 inches have on the intensity of the primary beam? This is the same question, isn't it? Mm-hmm. You'll see I have some repeats. Now, I'll answer that for everybody. SID has no effect on the primary beam. All other factors remaining the same, as tissue thickness decreases, which of the following will occur? Now we're asking density and we're talking contrast. So tissue thickness goes from thick to thin. What's going to happen to density? It's going to increase. What's going to happen to contrast? Decrease. It's going to increase. Mm-hmm. Both will increase. Because remember, as tissue, atomic number, density or thickness increases, contrast decreases, and it's because we have more scatter production. With all other factors remaining unchanged, what effect will a 15% increase in kVp followed by a 50% decrease of mass have on the primary beam? That's a complex question, isn't it? Here's how I break this down. We have intensity, we have energy, we have kVp, and after this week's lab, you probably have this a little more in your head, because we did a lot of this yesterday, didn't we? 15% increase in kVp, 50% decrease in mass. You just have to break these down and do them one by one. If I increase my kVp by 15%, what happens to the intensity of my beam? 100%. It increases 100%. So we'll go, I'll put double. Okay, what happens to the energy of my beam if I increase kVp? Remember, kVp is the only prime factor that affects the energy of the beam. It controls the energy of the beam, and it's a direct relationship. So my energy is going to increase. That would make no logical sense, would it? Okay, if I decrease my mass in half, what's going to happen to the intensity of my beam? It's going to cut it in half. What's going to happen to the energy of my beam? Nothing. So intensity would remain unchanged and would increase. Does that make sense? Intensity will increase, and F, overall beam energy will be greater.
Intensity would stay the same, though, right?
That's what I meant. Intensity would stay the same with E and F are the correct answers. What happens to the overall percentage of Compton and PE inter KVP is increased? And there was a question that came up in the earlier session. What happens, if you notice when I say this, they said, hey, Monica has a slide that says this, and that is that Compton will decrease. That's when you get way up in energy, way up there. But the reason it does decrease, if you notice when I say this, I go Compton and transmission will trend up with an increase of KVP, and PE will trend down. Yeah. So Compton increases, PE effect decreases. This is from a different author, a different physicist. That Monica's using, it's Kenny Bouchon, and he thinks on this level that's, you know. Which of the following techniques will produce the highest receptor exposure? This is really just a pretty simple, if you remember, and when you get to the question and you remember, oh yeah, I just figure out what mass is, okay? So if we take 800 MA and 0.25 seconds, we end up with 200 mass. We have 200 MA 1 second, that would be 200 mass. We have 500 MA and half a second, would be 250 mass. We have 500 MA and 100 milliseconds, that's 50 mass. The highest mass wins. Okay, the interaction of X-ray photon and matter that causes a change in direction and energy of the photon is defined as, it's not attenuation, is it? But it's one of the interactions of the attenuation. Photoelectric interaction, you don't have any photon left. Bremsstrahlung is in the tube. Scattering would be the correct answer. Which scatter would it be in specifically? Compton. If one wishes to decrease IR exposure by 15% or 50%, which of the following adjustments would be most appropriate? Half the mass. Half the mass. Would this work? It would, but it's not the most appropriate. With a decrease in KVP without compensation of mass, which of the following will occur? Okay, so we decrease KVP. Now, you want to read these carefully because guess what? There's another question that says with an increase in KVP. Okay, so what happens to density if we decrease KVP? It decreases. It's a direct relationship. What happens to contrast as we What happens to contrast if we have a thinner part? It's going to increase. So it would be radiographic density and contrast will no. D, radiographic density will decrease and contrast, yep. Right there. With all, do you see where you have these conceptual questions? That's what you're struggling with. That's normal. If you remember the first day of class, I did a poll in here. How many of you are tactile learners? And just about everybody raised their hands. You know, I loved anatomy lab, but I hated physiology. That's where we fall. Know where nurses fall? They hate the anatomy lab, but they love the physiology. Yeah. And that's why they become nurses. With all other factors remaining unchanged, what effect will a decrease of mass have on the primary beam? Okay, if we decrease the mass, what's going to happen to the intensity of the primary beam? It's going to decrease. What's going to happen to the energy of the beam?
Nothing.
Nothing. Nothing. This is just a rote memorization one. This is a rule of thumb. And that is the minimum technical change necessary to cause a visible shift in density is a blank % adjustment of mass. 30% to get a 20% shift. All of the following, except the affect exposure rate or intensity of the primary beam. Okay, so we're talking about the number of photons in the primary beam. If I change my exposure field size, does it have an effect? Because we're allowing more photons out of the tube. Milliamperes, okay? If I change my MA, it's changing my mass. Will that change the intensity of the primary beam? Certainly. Kilovoltage, same thing. Distance. Here again, keywords right there. I think the reason I have repeats in here is the year before I had my most missed, and I just kind of saved that as last year's and then take out, you know, questions and add questions. And I was probably in a hurry. We already did this one. Do you want to talk about this one anymore? No? When an X-ray photon undergoes a non-ionizing, this is a good question. When an X-ray photon undergoes a non-ionizing scatter interaction, the ejected electron is called a D. A non-ionizing, so there's no electron ejected. What's an Auger electron? Is that characteristic? Yeah, characteristic. And that's named after a scientist.
Where does recoil come from?
Recoil is Compton.
Okay.
And what's the other name for recoil? Compton electron. Okay. And where does photoelectric come from? I mean, yeah, I said the answer. Photoelectron comes from a photoelectric interaction. Oh, this is tough. The sum of the kinetic energy transferred to the ejected electron, its binding energy, and the scatter photon energy equals the incident photon energy. What kind of interaction is this? Well, I think we wrote this out one time. So we have energy, kinetic energy given to the ejected photon, or excuse me, the ejected electron, plus that electron's binding energy plus the scatter equals the energy of the incident. Right there. Now, you want to know what this one looks like? This would be the energy the kinetic energy given to the electron plus the binding energy equals the energy of the incident photon. That would be photoelectric.
Is that in your notes, by any chance?
I think so. Yeah, I know it's in the book.
Okay.
Oh, I just did that one. The sum of the binding energy of the electron and the kinetic energy transmitted to it equals the incident photon energy. That's photoelectric. Well, this is a good one. Okay, I wish I could say that I wrote this question, but this is a Carlton's question. How do I remember that? I have no idea. But X-ray photon energy is inversely related to, okay, the applied or selected MA. No, if I increase my MA, what happens to my intensity? It increases. The KVP, if I increase KVP, what happens to the intensity? It increases. The intensity of the X-ray beam, that's completely bogus there, because anyhow, it's going to be photon wavelength. Look at these wavelengths. This would be high energy. This would be low energy. So as the wavelength gets shorter, the energy is going to get higher. Now, this is just the backwards one of the other one. If one wishes to increase IR exposure 100%, which of the following would be most appropriate? Double your mass. Isn't this a good learning tool right now?
Yeah. I thought your primary goal is to have the lowest mass possible, and still get a good image.
Right, but like if you're doing a project and you shoot it and it's not enough IR exposure, you're going to adjust mass. You want to use as little as possible, but you want to have enough. Okay, the intensity of ionizing radiation increases as the distance from the source of the radiation decreases, the distance from the source of radiation increases, the frequency increases. Frequency doesn't have anything to do with intensity, or the wavelength decreases. This is a Carlton's question. It's going to be A, the distance from the source of radiation decreases. In other words, you shorten your SID. You notice it doesn't say primary beam. With all other factors remaining unchanged, what effect will an increase of mass have on the primary beam? Okay, so if I increase my mass, increasing my mass, what's going to happen to the energy of the beam? Nothing. It's going to remain unchanged. Okay, so energy will remain unchanged. What's going to happen to my intensity? It's going to increase. So C and F. Bone produces image receptor blank. Bone produces less image receptor blank because it attenuates the X-ray beam more than soft tissue does. Exposure, correct. Right there. Any questions on that one? The spreading of X-ray photon intensity as it exits the X-ray tube is termed, excuse me, divergence. What's that?
When I took it, I think I was reading through them too fast because that time.
Yeah, that's, you're gonna have 15 more minutes, which should be adequate.
I was doing one, I had no idea what I was doing wrong.
A radiograph that demonstrates minimal differences between densities is called minimal differences, okay? Here's high contrast, black, white, and stretch them out, black, white, and then we have all these steps of gray in between. That's long scale, okay? What's another name for long scale contrast? Decreased contrast. Short scale and high contrast would be increased contrast. Contrast is that you should have taken the blue pill sort of effect. The matrix, yeah. With a decrease in KVP without compensation of mass, which of the following will occur? Decrease, well, we've had this one. Do you want to go through this one again? Okay. When an X-ray photon is absorbed, the ejected electron is called a photoelectron. Oh, there we go. What's that? What questions do you all have?
Oh,
Yes.
questions in the contrast question that like pick the options?
Yes.
Yeah, we don't
That
like.
beauty.
Yeah.
The second
Okay.
one. Second one.
Okay, is dependent upon subject contrast and film contrast. That is going to be image contrast. Was that one of the choices?
You hope so.
It's better contrast, light contrast,
Radiographic. Yes.
radiographic contrast, yeah. Okay. Is the range of differences in intensity of the attenuated beam. That is subject contrast. Subject contrast. Because remember, it's the aerial image. You have that primary beam. Here's what I see in my head, is I see a primary beam like a spotlight coming out of my X-ray tube. It hits my patient and my patient becomes a disco ball, mirrored balls. And you have attenuation, and then the beam comes out of them in all sorts of different directions, and it's at a lower energy state and lower intensity. And that is subject contrast. How did the subject affect it? Many densities with very little difference from step to step. That would be low contrast, okay? Is dependent on KVP and amount and type of irradiated material. That's right out of the notes. That is going to be subject contrast. Subject contrast. It provides sufficient difference in density among the various details to make them distinctly visible in all areas of the radiograph. Optimum. High, low, and optimal contrasts are all types of radiographic. fewer densities with greater differences from step to step. It's going to be high contrast. High contrast, yeah, right there. Okay, so yeah, whenever it's asking contrast, you don't even look at the mass. It has nothing to do with it. It's going to be KVP, low contrast, high KVP, low KVP, high contrast. Now, what about the greatest density? Now we can calculate this. These are roughly 15% apart here and here, right? So I'd say, hey, we need to go to, we're going to make a common KVP of 80 KVP. So in order to do that, I'd have to add 10 KVP, right?
Yeah.
So I'd add 10, and we end up with 80 KVP here. But what just happened to my density? It just doubled it, didn't it? So we have the mass. Well, sometimes when you get beat up, you know, and I didn't do it on purpose, but sometimes when you get beat up and then you go back over it, you go, oh, I see what I did, you know, and it's a good learning experience. That will stay, that will stay. We're going to have to subtract 10 to get us to 80. What just happened to my density? It have to
Oh, I'm in for the mass, you have to double it now.
double the mass.
I was jumping in.
Now, we're all common here, 80s, so now we just look here and we go, yep, this would be the highest density right there. Okay? We have a few minutes. Do you want to work a big problem? Or are there any specific equations you'd like to work out? Everybody feels comfortable with the equations? Okay.
Patient thickness. Having a problem.
Okay, okay.
It's like, I don't know, 'cause I feel like on like the notes and stuff, there's like quite a few like rules or whatever that you have to follow,
Mm-hmm.
and I'm getting like confused with when to use.
Okay.
which I guess.
Well, what's going to determine this is going to be, is it fixed or variable KVP? You know, and so with variable KVP, we're going to use KVP, 2 KVP increase or decrease for every centimeter change, right? And then with mass, it's going to be 20% increase for every centimeter, and this would be a fixed KVP system. And we would subtract 10% for every centimeter. So you want to work a couple? Okay, so we'll go variable KVP. We have 70 KVP, and we have a part thickness of 18 cm. Part thickness, it swells up, and so now it's 21 centimeters. So what I'm going to do is take 21 cm minus 18 cm is going to equal 3 centimeters. And I'm going to take 3 centimeters times 2 KVP per centimeter equals 6 KVP. So then we'll come over here and we're going to have plus 70 KVP equals 76 KVP. Just like that. Now you do just the opposite. You would subtract it if it was thinner. All right? So this is what happens, you know, that technique chart that you're building right now, is you're gonna look at your wrist, and you're gonna look at your patient's wrist, and you're gonna say, hey, they're about a centimeter thicker than mine. Just add 2 kVp and you're golden. Okay, so you want variable? I mean, fixed. Okay, so we have 20 mass and part thickness of 17 cm. Patient comes back, they have a part thickness of 19 cm. I'm going to take 19 cm minus 17 cm equals 2 centimeters increase. I'll take this times 20% per cm. It's going to equal 40%. Take 20 mass times 0.4 equals 8 mass. I take 20 mass plus 8 equals 28 mass. There. Does that help?
Yeah. Do you ever use a fixed BBP system in like live?
Mm-hmm.
Okay.
Yeah.
Because I was like asking the TAs yesterday during lab, like with our sheet, and I was like, how do I know if this is specifically like what I'm calculating is variable or like fixed? And they said that it's usually always variable.
For extremity work, it's usually always variable. When you get torso work, you're going to be using fixed a lot of times. Mm-hmm. Yeah, I like using, when we're developing techniques, I like using variable because it's easy, quick, right?
When we're doing stuff like that, we did our first exam, and then when they come in for their post-op, how do we know? Is it already measured, or are we gonna be measuring that part?
You would measure
Or are we just estimating
it. Estimating. Mm-hmm. That's what's going to end up happening. When you go into your externship and you ask for calipers, they're going to laugh at you. But you, as a student, you really should measure so until you get an eye for it. And then you're going to get, you're not going to have to measure nearly as much because you're going to have techniques on you.
How do you go about estimating part thickness increase if there's a cast? You just look at their other arm, and then is there a certain amount of?
It's not that critical. Remember, how much of a change are we going to have in density if we shot and then increase our, and we just keep the part thickness the same, we increase our mass 40%.
It's not even.
It's not that much, right? And so we're just trying to compensate for that little extra thickness. So I think the easiest technique system to use is what we're developing right now, except when you get out on your externship, you're going to have to build another one. And the best way is you go to the tech and say, hey, what would you shoot for my wrist? What would you shoot for my, and then you'll have a rough idea. And then you just go in and you go, oh, that little kid's femur is the size of my wrist. Mm-hmm. And you would use that technique. So there's a lot of just, you don't think about everything you do in the car when you drive anymore, do you? Mm-hmm. But you did before. You had to concentrate on absolutely everything. And that's what it's going to be like. Yeah. Any other questions, sir?
When it decreases, you
Yes. Okay, so we'll go fixed. We'll go 30 mass. And part thickness of 35 cm. And they come back and they're 32 cm. Or, you know, your part thickness is 35 cm and then you estimate the patient's at 32, is how you can look at it. So we're going to take 32 minus cm minus 35 cm equals a -3 centimeters. Take -3 times 10% decrease, or 10% per cm equals -30%. Okay. And so then we're going to take 30, -30%. Here, which would be a -0.3 times 30 mass equals a -9. Take -9. There you go. Just like that. Everybody cool?
When are we doing the part 2 of our?
We'll do that next week. I forgot all about it. I've had so many other things on my plate. My memory is about that long right now. I'll get those printed up though.